A U.S. Navy aircraft carrier operates in total isolation on the open ocean. It is a 4-acre steel grid loaded with billions of dollars of aviation hardware, completely detached from the physical infrastructure of the mainland. During a nighttime launch cycle, the environment reaches absolute maximum intensity. You have sailors working inches from intake turbines, dense steam blinding the crew, and 70,000 pounds of thrust launching metal into the dark. At any given moment, the deck must coordinate up to 70 aircraft, 5,000 personnel, live high-explosive ordnance, and the ship's nuclear propulsion systems. All of this happens on a runway that is only 300 feet long. The tower is moving at 30 knots, and the entire surface is constantly pitching and rolling with the ocean waves. No team of humans can track that volume of highly volatile, intersecting agents using intuition alone. Relying on visual coordination in an environment this dense mathematically guarantees a collision. The flight deck forces a strict engineering constraint. It is an extreme edge computing environment where a single millisecond of data latency or physical desynchronization results in loss of life. To solve this, you have to look beneath the deck. Deep within the hull of the ship sits a heavy iron server infrastructure, heavily shielded from the violence occurring above. These servers are constantly flooded by rapid-fire data streams, pulling telemetry from the cowering sensor arrays and communication antennas mounted on the island. They ingest precise navigation data from the JPAL system, continuous transponder pings from every jet, and complex maintenance status codes directly from aviation mechanics. Because the ship operates in combat environments, this data pipeline has absolute zero tolerance for failure. If the processing lags, the deck stops functioning. The system strips away the deck's physical chaos by applying a deterministic, rules-based state machine. Every mechanical action is translated into a rigid sequence of computational logic. Operational survival depends entirely on the flight deck control database. It turns an intensely dangerous, unpredictable physical space into a mathematically controlled digital matrix. Historically, the Navy tracked aircraft using the Ouija Board, an analog system where crew manually position physical scale models across a transparent deck map. It is an iconic piece of naval history, but a plastic model cannot cross-reference live fuel consumption rates with incoming atmospheric data. An analog board cannot integrate multi-layered data streams. The digital replacement is a massive ingestion architecture, routing real-time sensor data over deterministic message buses. Hard-coded redundancies ensure data instantly reroutes if physical hardware is destroyed. Furthermore, strict red-black separation ensures highly classified mission data never intersects with unclassified mechanical telemetry. Inside this single authoritative picture, an aircraft is no longer treated as a physical vehicle. It becomes a persistent, dynamic object model. This is the exact database schema that governs every aircraft on the flight deck. It proves how the object model maps to physical reality. Fixed metadata fields like tail number and aircraft type establish the baseline parameters. They tell the database exactly what mass and dimensions it is managing. Beneath those are the dynamic state fields. Taxi clearance, wingfold state, and engine state are booleans and enums flipping from true to false, on to off, in constant synchronization with the active deck. The digital and physical domains are directly linked. When a deck crew member commands a jet to roll forward 20 feet, that physical movement instantly updates the spot location row. By trapping every jet inside this strict database logic, the system enforces a hard limit. An aircraft physically cannot execute an action if its current digital state does not explicitly permit it. The database logic extends to the environment itself. The 4 acres of steel are digitally subdivided into rigid geospatial constraints, mapping out no taxi zones, jet blast hazards, and foul lines. The system cross-references every aircraft's coordinates against these zones in real time to prevent intersection. This includes direct integration with the ordnance management systems. The database tracks live weapon locations against thermal and electrical hazard zones, eliminating the possibility of catastrophic mishandling. The geometric rules are absolute. If a parked aircraft breaches a foul line while the arresting gear is cycling, the database forces an immediate wave-off command to the incoming jet. This is geospatial database logic executed at sea. It acts as an invisible force field, preventing multi-million-dollar jets from inadvertently destroying one another. A carrier continuously cycles between two highly conflicted operational modes, launching aircraft out and recovering aircraft back in. The launch scheduler algorithm manages the outbound queue. It calculates catapult availability, strictly categorizes aircraft weight classes, and factors in real-time wind over deck telemetry to optimize the firing sequence. But the recovery scheduler can instantly assert dominance. If a returning jet flags a low fuel emergency, the recovery algorithm calculates cycle time and aggressively overrides the launch queue to clear the deck. Both of these schedulers are built entirely on deterministic, rules-based logic. Given the exact same inputs, the system will yield the exact same output every single time. This highlights a critical architectural boundary. The system operates on strict, predictable calculations, and probabilistic guessing models are completely forbidden from operating inside this specific control loop. When you are operating heavy machinery over the ocean at night, you cannot afford algorithms that guess. Predictability is exactly what ensures survival. All of these systems, the fail operational ingestion pipeline, the strict object model schema, and the geospatial schedulers, converge at the exact moment of launch. At that millisecond, the database authorizes an immense release of physical, mechanical power. If the invisible choreography of this network failed, that concentrated energy would instantly fracture the deck's operations into cascading failures. Pilots do not avoid fuel starvation and ordnance accidents by luck. They survive because of flawless, deterministic data integration. The carrier functions as a mission-critical edge data center, synchronizing steel, fuel, and human calculation into a single cohesive weapon. Host 1. Ultimately, the chaos of the flight deck is an illusion. Beneath it is a deterministic fail operational database executing strict geospatial constraints in real time. It's the invisible choreography engine of naval aviation. Thanks for joining.